On a Thursday morning in early June 1940, the telephone rang in an executive office at Chrysler headquarters in Highland Park, Michigan. The building itself was a monument to American automotive ingenuity, designed by Albert Kahn decades earlier, its floors humming with the productive energy of thousands of workers assembling automobiles. Kaufman Thuma Keller, the chief executive of Chrysler Corporation, picked up the receiver expecting another routine business call. What he heard instead would set in motion one of the most remarkable industrial transformations in human history. The voice on the other end belonged to William Knudsen, a Danish immigrant who had risen through the ranks of American industry to become one of the most respected manufacturing minds in the country. President Franklin Roosevelt had just appointed Knudsen as Commissioner of Industrial Production, tasking him with the impossible job of preparing America's peacetime industries for what increasingly looked like inevitable war. Knudsen was a practical man who spoke in the clipped, efficient manner of someone who had spent decades on factory floors. He wasted no time with pleasantries. The conversation that followed lasted precisely 7 minutes. In those 7 minutes, Knudsen laid out a challenge that seemed to border on the absurd. The United States Army needed tanks. Not a few dozen tanks for training purposes or ceremonial parades, but 1,000 medium tanks, complex 30-ton machines of war that represented some of the most sophisticated mechanical engineering of the era. And Knudsen wanted Chrysler to build them. Keller, a man known for his blunt honesty and engineering pragmatism, gave an answer that would have horrified a politician, but perfectly captured the spirit that would make the entire program possible. He told Knudsen the simple truth. He had never seen one of these things. Chrysler made automobiles, trucks, engines, transmissions. They built civilian products for civilian markets. Tanks were military equipment, assembled in government arsenals by specialized craftsmen using methods unchanged since the Great War. The gap between what Chrysler knew and what Knudsen was asking seemed unbridgeable. But Keller did not say no. Instead, he said he did not know if it was possible, which was an entirely different thing. Not knowing left room for discovery, for investigation, for the systematic application of engineering principles to novel problems. This distinction between cannot and have not yet figured out how would prove crucial to everything that followed. When Keller hung up the telephone, he sat for a moment considering what he had just heard. The audacity of the request was matched only by its urgency. Europe was burning. The German military machine had demonstrated a new kind of warfare, one that relied on massed armored vehicles moving with speed and coordination that shattered traditional defensive lines. Poland had fallen in less than a month. Denmark and Norway had been overrun in weeks. France, the great military power of Europe with its supposedly impregnable Maginot Line, was at that very moment collapsing under the weight of panzer divisions that struck with terrifying speed and overwhelming force. The mathematics of the situation were grim and getting grimmer by the day. American military planners had finally begun taking inventory of the nation's actual military capabilities, and what they found was sobering enough to qualify as terrifying. The United States Army, the military force of a nation of 130 million people with the world's largest economy, owned exactly 66 medium tanks. Not 6,600, not 6,600. 66 individual vehicles. The German military had deployed more than 3,000 Panzers across Europe in just over a year. They were producing more tanks every month than America possessed in total. The comparison went beyond mere numbers. American tanks were themselves obsolete, based on designs from the previous decade, mounting weapons that would be inadequate against modern armor, using engines that were underpowered and unreliable. The few American tanks that existed had been assembled slowly, carefully, by hand, in government arsenals where master craftsmen fitted each component individually. Each tank took months to complete. Each tank was essentially unique, with hand-fitted parts and custom adjustments that made standardization impossible. American military power had been allowed to atrophy through 2 decades of peace and budget constraints. The nation ranked 19th in overall military capability, behind countries like Portugal and Romania. The army had more horses than tanks, more cavalry officers than armor specialists. The institutional knowledge of how to wage modern mechanized warfare simply did not exist, and time was running short. Every week brought fresh reports of German victories, of Allied defeats, of the seemingly unstoppable advance of a military machine built around coordinated armored assault. Keller understood all of this in general terms, though the specific details would emerge only gradually. What he understood immediately was that traditional approaches could not solve this problem. If America needed 1,000 tanks in 18 months, and current production methods produced perhaps 3 tanks per month at maximum capacity, the arithmetic was impossible. You could not train enough specialized craftsmen. You could not build enough government arsenals. You could not hand-fit enough components. The traditional approach guaranteed failure. Within an hour of ending the call with Knudsen, Keller had assembled his top engineering minds in his office. B.E. Hutchinson, Chrysler's chief engineer, was a methodical problem solver who approached every challenge with systematic rigor. Frank Zader, vice president of engineering, was known for his innovative thinking and willingness to challenge conventional wisdom. Together, these 3 men formed the core of what would become the most ambitious military-industrial program attempted to that point in history. The initial conversation was remarkably brief. Keller explained what Knudsen wanted. Hutchinson and Zader listened without interruption. When Keller finished, there was a moment of silence as the engineers processed what they had heard. Then Hutchinson asked the question that cut to the heart of the challenge. What was the current production timeline for a single tank? Zader had already been doing preliminary research, anticipating that the war in Europe would eventually require American industrial involvement. He had contacted the Rock Island Arsenal in Illinois, the primary government facility for tank production, and gathered information about their methods and capabilities. What he learned was not encouraging. The arsenal could produce 3 M2A1 medium tanks per month when operating at full capacity. Each tank required 12 weeks from initial components to final acceptance testing. The process was entirely manual, relying on skilled workers who understood how to adjust and fit components that were manufactured to loose tolerances. Hutchinson pulled out a notepad and began calculating. If you needed 1,000 tanks and could produce 3 per month, you required 333 months of production time. That was nearly 28 years. Even if you could somehow triple production capacity through heroic effort, you were still looking at 9 years. The Army wanted delivery to begin in 18 months. The disconnect between requirement and capability was so vast that it seemed to mock any attempt at resolution. But Keller saw something that military planners had missed. He recognized that the problem had been framed incorrectly. The Army was asking how to build more tanks using existing methods. That was the wrong question. The right question was how to build tanks using entirely different methods. Keller said something that would become a kind of mantra for the entire program. We don't build tanks the Army's way. We build them our way. This statement represented more than bravado. It embodied a fundamental insight about industrial production. Chrysler manufactured 3,000 automobiles per day at the Highland Park plant. An automobile was a complex mechanical assembly comprising 5,000 individual components that had to fit together with precision. Those components were manufactured by hundreds of suppliers, shipped to the assembly plant, and combined on moving production lines by workers who performed specialized tasks repeatedly. The entire system worked because every component was manufactured to exact specifications that allowed interchangeable parts. You could take any engine block and it would fit with any crankshaft. You could take any body panel and it would mount properly on any frame. Tanks were built the opposite way. Components were manufactured with wide tolerances, then skilled workers fitted them together through a combination of experience, judgment, and manual adjustment. Every tank was unique. Parts from one tank would not necessarily fit another tank. This made sense in a world where you were building a few dozen tanks per year and employing master craftsmen who had learned their trade over decades. It made no sense whatsoever in a world where you needed thousands of tanks in months and would be training workers who had never seen a tank before. The three men decided they needed to see tank production firsthand before making any commitments. Within days, they travelled to Rock Island Arsenal to observe the manufacturing process. What they witnessed was simultaneously impressive and disturbing. The craftsmen working on tanks were clearly skilled, demonstrating expertise built over years of practice. They worked with confidence and precision, fitting armor plates by eye and experience, adjusting track tension through subtle mechanical understanding, machining parts on manual lathes to exact specifications determined on the spot. But the process was impossibly slow and utterly dependent on individual expertise. Keller watched a worker spend 40 minutes hand-fitting a single armor plate, filing down high spots and shimming low spots until the plate sat correctly. He watched another worker adjust a suspension component by tightening bolts incrementally, checking clearance repeatedly, making micro-adjustments based on feel and experience. This was craftsmanship of the highest order. It was also completely unsuited to mass production. The current tank being produced was the M2A1 medium tank, a 19-ton vehicle mounting a 37mm gun and several machine guns. The armor was riveted construction, which created substantial labor requirements and concerning structural vulnerabilities. Rivets required drilling holes, inserting fasteners, and hammering them tight, with each rivet representing a potential weak point. The internal layout was cramped, the visibility was poor, and the overall design reflected compromises between what was militarily desirable and what was mechanically feasible with hand assembly methods. Each M2A1 required approximately 8,000 individual components. None of these components were manufactured to the kind of precision tolerances that would allow truly interchangeable assembly. A transmission housing from one tank might fit perfectly into another tank, or it might require hours of adjustment and modification. You simply could not know until you tried. This variability meant that experienced workers were essential. A novice could not successfully assemble a tank because the work required constant judgment calls about how to make imperfect components work together. Keller turned to Hutchinson as they walked through the arsenal and said something that captured his assessment perfectly. "This is not manufacturing, this is sculpture. Every tank is a custom creation. You cannot scale sculpture, you cannot train sculptors quickly, and you certainly cannot produce 1,000 sculptures in 18 months. The trio returned to Detroit and immediately established what they internally called the Tank Committee. This working group met daily, often late into the night, in a commandeered conference room at the Highland Park facility. The committee included Owen Skelton, Chrysler's chief production engineer, along with specialists in tooling, metallurgy, logistics, and factory layout. Their mission was straightforward: determine whether Chrysler could produce tanks at scale, and if so, how. The breakthrough came from inverting the fundamental question. Instead of asking how to build tanks faster using existing methods, they asked how to build tanks differently using proven automotive principles. Skelton articulated this insight with characteristic clarity. An automobile weighs 2,000 pounds and contains 5,000 parts. Chrysler produces 3,000 automobiles daily. A tank weighs 30,000 pounds and contains 8,000 parts. The only meaningful difference is scale, not fundamental nature. Both are mechanical assemblies. Both can be built using the same production philosophy. This reframing changed the entire approach. If a tank was just another mechanical assembly, then all the lessons learned from decades of automobile mass production could apply. But this required completely reconceiving tank manufacturing from first principles. Every component would need to be redesigned for precision manufacturing. Every assembly sequence would need to be optimized for line production. Every quality control step would need to shift from craftsman judgment to measurable specification. The entire production philosophy would need transformation. The Tank Committee began systematically analyzing the M2A1 design to identify where time was actually spent during production. What they discovered was revealing and frustrating. Approximately 60% of total production time went to fitting and adjustment activities. Workers were not primarily assembling tanks. They were primarily correcting for the imprecision of the components being assembled. Parts manufactured to loose tolerances arrived at the assembly floor, requiring constant modification to fit together. This was where the 12-week production timeline came from. Most of that time was adjustment, not assembly. Hutchinson proposed what seemed like a radical solution, but was actually just the application of automotive practice to a new domain. Manufacture every component to automotive tolerances. When parts are precisely made, they fit together without adjustment. This eliminates the need for skilled fitting. It transforms assembly into a series of straightforward operations that can be performed by trained workers following clear procedures. The military engineers consulted about this approach were skeptical to the point of hostility. Automotive tolerances were adequate for civilian vehicles, but supposedly insufficient for military equipment. Tanks faced stresses and conditions that automobiles never encountered. The precision manufacturing required for interchangeable parts would need entirely new tooling, new supplier capabilities, and new quality control systems. It would cost more per component. It would require extensive engineering work to redesign thousands of parts. But Hutchinson had done the mathematics. Yes, each precisely manufactured component might cost slightly more than a loosely toleranced part, but the total labor required for assembly would plummet. A tank requiring 500 man-hours with hand-fitted components could be assembled in perhaps 150 man-hours with precision parts that simply bolted together. The labor savings vastly exceeded the component cost increases. More importantly, precision components made training new workers feasible. You could teach someone to install a precision-manufactured transmission mount in days. You could not teach someone to hand-fit a loosely toleranced mount in months. Skelton extended this thinking to the assembly process itself. If they were treating tank production like automobile production, they needed an automobile-style assembly line, not a series of stationary workstations where teams of craftsmen gathered around a tank for days or weeks. A moving line that brought work to stationary workers, each performing specific operations before the tank moved to the next station. This would require careful sequencing of operations, precise timing of component delivery, and standardization of tools and procedures. But it would also create a production system that could be scaled, measured, and continuously improved. By November 1940, the Tank Committee had developed what they called the Chrysler method for tank production. The method specified that every major component would be manufactured to precision tolerances using automotive machine tools. Armor plates would be standardized and interchangeable rather than hand-fitted. The hull would be welded using production jigs that positioned plates exactly rather than relying on skilled welders to align components by eye. The turret would mount on standardized rings with precise dimensions. The drivetrain would incorporate as many existing automotive components as possible. And final assembly would occur on a moving line with specialized workstations, each designed for specific operations. Keller presented the Chrysler method to the Army Ordnance Department in late November. The reception was chilly. Military engineers raised objection after objection. Automotive tolerances were insufficiently robust for combat conditions. Moving assembly lines would create quality control nightmares. Welded armor was inferior to riveted construction. The proposed production rate of 10 tanks per day was pure fantasy, disconnected from any realistic assessment of manufacturing capability. Several officers stated flatly that the plan would fail and that Chrysler was wasting everyone's time. Keller listened to these objections patiently, then posed a question that cut through all the technical debate. The Army needed 1,000 tanks in 18 months. Could the Ordnance Department produce them using traditional methods? Could any existing arsenal meet that requirement? Could any combination of government facilities deliver what was needed in the time available? The answer, unspoken but obvious, was no. The current production system could not possibly meet the requirement. Traditional methods guaranteed failure. The Chrysler method might fail, but it at least offered a chance of success. When the only alternative is certain failure, even an uncertain approach becomes compelling. In late November 1940, Chrysler received a contract unlike any previously issued. The government would pay for construction of an entirely new factory purpose-built for tank production. Chrysler would design, equip, and operate the facility under government oversight. The contract included one unusual requirement that reflected the scale of ambition involved. The Army insisted that the new factory be designed by Albert Kahn, the architect who had revolutionized industrial building design and made modern mass production physically possible. Albert Kahn was 71 years old in 1940, a small man with enormous influence over how American industry actually functioned. He had come to America from Germany at age 11, a Jewish immigrant fleeing the economic chaos of post-unification Germany. He had never attended architecture school, learning his profession as an apprentice in a Detroit firm while teaching himself through books and observation. By 1940, his firm employed 600 architects and engineers and had designed nearly one-fifth of all architect-designed factories in the United States. Kahn's genius lay in understanding that a factory was not simply a building that housed manufacturing equipment. A factory was itself a machine, a carefully designed system that enabled efficient production. His designs maximized natural light to reduce eye strain and improve worker visibility. They optimized material flow to minimize transportation time and handling costs. They created column-free open spaces that allowed flexible production layouts that could adapt as processes evolved. He pioneered the use of reinforced concrete, which allowed larger spans and faster construction than traditional steel frame buildings. Kahn's previous work included the Ford Highland Park plant, where the moving assembly line for automobiles was first implemented, and the River Rouge complex, which represented the ultimate expression of vertically integrated mass production. These facilities had made American automotive dominance possible by translating manufacturing principles into physical form. Now Keller was asking Kahn to perform the same service for tank production. The requirements that Keller laid out in early July 1940 seemed almost contradictory. The facility needed to be massive enough to house a complete tank assembly line, plus all component manufacturing operations. It needed to be built in months rather than years to meet the Army's aggressive timeline. It needed to be defensible against potential sabotage or attack. And it needed to be convertible to civilian production after the war ended, because the government was not interested in maintaining specialized military facilities during peacetime. Kahn accepted the commission and threw his entire firm at the challenge. Teams of architects and engineers worked 18-hour days producing drawings for what would officially be designated the Detroit Arsenal Tank Plant. The main building would measure 1.25 million square feet under a single roof, making it one of the largest industrial structures in the world. The design incorporated defensive features unusual for American industrial construction, including reinforced concrete walls in critical areas thick enough to withstand bomb hits, and a roof structure designed to deflect blast effects away from windows and ventilation systems. The facility's layout embodied the production philosophy that Keller and his team had developed. A main assembly line would run nearly the entire length of the building, roughly a quarter-mile. Feeder lines would deliver major components to the main line at precisely timed intervals. Machine shops would occupy the northern sections, producing drivetrain components and precision parts. Welding bays would fill the southern sections, where armored hulls and turrets would be fabricated using production jigs. The entire design allowed materials to flow in one direction only, from raw steel entering at the west end to finished tanks rolling out the east doors. Kahn's plans included one innovation that military engineers had never considered, but that reflected deep understanding of production requirements. The assembly line would be sunken below the main floor level, creating a trench approximately 4 feet deep running the length of the building. Tanks would ride on special carriers within this trench, allowing workers to access the underside without jacks or lift equipment. This single design choice would save hundreds of hours per tank by making suspension and drivetrain installation far simpler and safer. On September 9, 1940, groundbreaking occurred on 113 acres of former farmland in Warren Township, just north of Detroit. The site had been selected for its proximity to Chrysler's existing facilities, which would allow transfer of expertise and equipment, and for its access to railroad lines that would be essential for bringing in materials and shipping out completed tanks. Construction began immediately, with multiple contractors working simultaneously in a carefully choreographed sequence. The pace of construction bordered on reckless. Foundation work proceeded even as final architectural details were still being refined. Walls rose while utility systems were still being designed. The roof went on before interior partitions were complete. This violated every normal principle of construction sequencing, but time was the overriding constraint. Every week of delay meant more months before the first tank could be delivered. The construction crews worked through weather that would normally halt operations, building through rain and early snow. By February 1941, the main building was structurally complete but far from finished. Walls were up, but many windows remained uninstalled. The roof was complete, but heating and ventilation systems were only partially operational. Nonetheless, Chrysler began moving equipment into the facility. Machine tools arrived by rail and were installed even as construction continued around them. Workers set up lathes and milling machines in sections of the building that still had exposed wall cavities and temporary lighting. The timing created an absurd situation. Chrysler had committed to delivering the first tank by April 1941. But the factory would not be fully complete until May at the earliest. Keller made a decision that would become legendary among his engineers. They would build the first tanks inside an unfinished building. Production could not wait for perfect conditions. This created working conditions during that winter that bordered on the barbaric. Michigan's February and March weather is brutal, with temperatures regularly dropping below freezing and occasional snowstorms that dump inches of accumulation. The Detroit arsenal had walls and a roof, but with many windows still being fitted and the heating system only partially functional, the interior temperature was barely warmer than outdoors. Workers assembled tanks while wearing heavy coats and gloves, their breath visible in the frigid air. The solution to the heating problem was improvised but effective. A steam locomotive was brought inside the building, its boiler providing localized heat to the immediate work area. The locomotive sat on temporary tracks, puffing steam into the cavernous space, while workers assembled America's first mass-produced tanks nearby. The image captured perfectly the spirit of determined improvisation that characterized the entire program. This was not careful planning. This was industrial will forcing reality to bend. Meanwhile, the engineering challenges of actually producing tanks were being solved through methodical analysis and testing. The drivetrain presented the first major obstacle. The M2A1's transmission had been designed for hand assembly by skilled mechanics who could adjust and adapt as they worked. Chrysler's engineers completely redesigned it using automotive principles, creating a unit that could be assembled on a dedicated line, tested as a complete module, and installed as a single operation. The redesign reduced assembly time from 40 hours to 4. The suspension system required similar fundamental rethinking. Tank suspension faced enormous stresses from the vehicle's weight and from the rough terrain military vehicles encountered. The M2A1 used a complex system of springs and linkages that required careful adjustment during installation. Chrysler's engineers standardized every component, created fixtures that allowed pre-assembly and testing before installation, and designed the mounting system for rapid attachment to the hull. Installation time dropped from 2 days to 6 hours. The armoured hull presented perhaps the greatest challenge and the most contentious disagreement with military engineers. Traditional tank hulls were riveted together from multiple armour plates, with each rivet requiring drilling, insertion, and hammering. This process took weeks of skilled labour. It also created a serious combat vulnerability. When a penetrating hit struck near a rivet line, The impact could shear rivets off inside the tank, turning them into deadly projectiles that killed or wounded crew members. Chrysler proposed all-welded hulls fabricated using production jigs that positioned plates precisely. The Army Ordnance Department objected with unusual vehemence. Welded armor had never been combat tested at scale. Welding created heat stress in armor plate that might compromise its protective qualities. And welding required highly skilled operators who took years to train. There simply were not enough qualified welders available to support the production volumes being discussed. Chrysler countered each objection systematically through testing and demonstration. They produced test welds and subjected them to ballistic testing that proved welded joints were actually stronger than riveted construction under combat conditions. They developed post-weld heat treatment processes that eliminated stress concerns while maintaining armor integrity. And most importantly, they demonstrated that semi-skilled workers could produce acceptable welds after just 2 weeks of training when using production jigs that positioned every piece perfectly and controlled every critical dimension. The jig system was crucial to making welded construction feasible. A massive steel framework held armor plates in exact position while welders worked. The jig absorbed the heat stress and prevented distortion. It ensured that every weld was made in optimal position, and it allowed multiple welders to work simultaneously on different parts of the hull without interfering with each other. The jigs were expensive and time-consuming to build, but they transformed welding from a craft skill into a production operation. By March 1941, component production was underway at multiple Chrysler facilities throughout Michigan. The tank that would roll out in April would be assembled from parts manufactured at plants in Detroit, Hamtramck and Highland Park, then shipped to Warren for final assembly. This distributed production system allowed Chrysler to leverage existing manufacturing capacity and expertise while the new arsenal was still being completed. The engine situation presented a creative engineering challenge that would result in one of the program's most unusual solutions. The M2A1 used the Continental R975 radial aircraft engine, a reliable 9-cylinder power plant that produced 400 horsepower. The engine was well proven and capable, but Continental could not produce engines fast enough to meet the projected production schedule. Chrysler needed an alternative power source. The solution came from Harry Wilson, an engineer with a reputation for unconventional thinking. Chrysler had recently developed a new inline 6-cylinder engine for potential automotive use. The engine was compact, reliable, and produced 115 horsepower from relatively simple construction. Wilson proposed combining 5 of these engines into a single power plant for the tank. The concept seemed absurd on its face. Linking 5 separate engines to drive a single output shaft created enormous engineering challenges around synchronization, vibration, and mechanical complexity. But Wilson and his team loved complex problems. Under his direction, they created what would become known as the A57 multibank engine. The design used 5 complete inline 6-cylinder engines arranged in a radial pattern around a central gear case. Each engine drove a gear that meshed with a central output gear connected to the transmission. The entire assembly produced 425 gross horsepower and 370 net horsepower from 30 cylinders displacing 1,253 cubic inches. The A57 was bizarre. It was complex. It had 5 carburetors, 5 distributors, 5 fuel pumps, and 5 cooling systems. It looked like something assembled by an enthusiastic amateur rather than professional engineers. Army ordnance officers called it a Rube Goldberg contraption and objected to its adoption. But the multibank engine solved multiple critical problems simultaneously. It used existing tooling and components, allowing immediate production without developing new manufacturing capability. It required no exotic materials or specialized parts. And it could be assembled by relatively unskilled workers following clear procedures and using simple hand tools. Most importantly, the A57 was available immediately, while the Continental engine faced production constraints. In the calculus of wartime manufacturing, the adequate solution available now beats the perfect solution available later. The multi-bank engine would power thousands of Sherman tanks and prove surprisingly reliable despite its unconventional configuration. April 12, 1941, one day before Easter Sunday. The Detroit Arsenal tank plant remained obviously unfinished. Portions of the building still lacked windows. Temporary lighting illuminated work areas. The heating system worked intermittently. But on the assembly line floor, the first Chrysler-built M3 medium tank sat complete. The M3 represented an evolution from the M2A1, mounting a larger 75mm gun in a hull sponson and a 37mm gun in a fully rotating turret. The design was already obsolescent, a compromise between proven technology and urgent necessity. But it was the first tank ever produced on an automobile-style assembly line. The formal delivery ceremony was scheduled for April 24th to allow preparation and to invite appropriate officials. On that spring day, the completed M3 was driven outside the still unfinished factory before a crowd of military officials, Chrysler executives, local politicians, and workers. Keller himself rode in the tank as it emerged into the sunshine, symbolically delivering on his promise from 10 months earlier. The demonstration that followed was carefully designed to impress skeptical military observers who still doubted whether production methods could create combat-capable vehicles. The 28-ton M3 accelerated across the proving ground adjacent to the plant, demonstrating surprising speed and maneuverability for such a large vehicle. It smashed through constructed obstacles, climbed steep grades, and forded a water obstacle. The 75mm gun fired several rounds, obliterating targets at range. As a finale, the tank drove straight through a mock-up farmhouse, reducing it to splinters and rubble. The message was clear. Production methods had not compromised combat capability. What the demonstration did not show was more significant than what it displayed. Behind that single completed tank was an entire production system unlike anything the military world had ever seen. The assembly line was now operational. Component production was ramping up at multiple facilities. Supplier networks were being established across Michigan and neighboring states. Hundreds of workers were learning their specialized tasks. The factory that had seemed impossible in June 1940 was becoming reality in April 1941. May brought steady production increases. One tank every other day at first, then one daily, then more. The learning curve was visible in the production data. Early tanks took longer to assemble as workers learned their operations and as engineers identified bottlenecks. But every week showed improvement. Assembly time per tank dropped. Quality problems decreased. The production system was optimizing itself through experience. Chrysler was simultaneously solving the supplier challenge that the entire program depended upon. A single tank required approximately 8,000 components. Chrysler could not manufacture everything internally. They needed hundreds of suppliers producing everything from track pins to periscopes, from electrical switches to armor plates. B.E. Hutchinson led the supplier development effort personally, traveling throughout Michigan, Ohio, Indiana, Pennsylvania, and Wisconsin. His pitch to potential suppliers was remarkably direct. "We need these parts made to these specifications in these quantities on this schedule. Can you do it?" Many suppliers initially balked at the requirements, which demanded precision manufacturing beyond their current capabilities and volumes that exceeded their existing capacity. But Hutchinson offered substantial incentives in return. Chrysler would provide technical assistance in developing the necessary tooling and processes. They would make advance payments for equipment purchases, and they would guarantee long-term contracts that made capital investment worthwhile. The supplier network grew throughout 1941, eventually encompassing more than 400 companies across 32 states. A foundry in Pennsylvania cast final drive housings. Machine shops in Wisconsin produced track pins and connectors. Forges in Ohio supplied armor plates. Electrical manufacturers in Connecticut made wiring harnesses and switch panels. This distributed production system created resilience. No single point of failure could shut down tank production. If one supplier faced problems, alternatives could be qualified and brought online. The workforce transformation paralleled the supply chain development. In June 1940, Chrysler employed exactly 0 workers with tank manufacturing experience. By August 1941, the Detroit arsenal employed 5,800 workers, the vast majority learning tank assembly from absolute zero knowledge. This created an enormous training challenge. How do you teach thousands of people to build something that almost nobody knows how to build? Chrysler's solution was to break tank assembly into small, specific operations that could be taught quickly. A worker assigned to install transmission mounts did not need to understand how transmissions worked or how tanks fought. They needed to know how to position a mount, insert bolts in the correct sequence, and torque them to specification. This could be taught in 2 days using training fixtures that replicated actual production conditions. Chrysler set up training schools where new workers learned their specific operations before touching an actual tank on the assembly line. This allowed rapid onboarding with minimal productivity loss. A new worker might be slow and tentative for a few days, but they quickly developed the muscle memory and judgment needed for their specific task. Within weeks, they were working at the pace of experienced operators. By September 1941, the Detroit arsenal was producing 4 tanks per day, a rate that would have seemed fantastical just 15 months earlier. The M3 medium tank was proving its worth in combat. British units receiving M3s under the Lend-Lease program nicknamed it the Grant, after Ulysses S. Grant. British tankers appreciated the Grant's reliability and firepower, though they criticised its high silhouette and sponson-mounted main gun, which limited traverse and made the tank unnecessarily tall. Chrysler engineers, working with Army Ordnance Department designers, were already developing the M3's replacement. They had recognised from the beginning that the sponson-mounted gun was a compromise forced by design constraints and manufacturing limitations. A better tank would mount the main gun in a fully rotating turret, allowing the crew to engage targets in any direction without turning the entire vehicle. The result was the M4 Sherman, which would become the most iconic American tank of the war and one of the most produced armoured vehicles in history. The M4 used the M3's basic hull and suspension system, but mounted a 75mm gun in a fully rotating turret. The design was developed with mass production as a primary consideration. Every component was designed for manufacturability. Every assembly sequence was optimized for line production. The Sherman was not the most heavily armored tank. It was not the most powerful tank. But it was designed to be produced in overwhelming quantities using industrial methods. The transition from M3 to M4 production demonstrated the flexibility that mass production methods provided. Rather than shutting down the entire facility to retool, Chrysler gradually substituted M4 components for M3 components as tooling became available. The assembly line continued operating throughout the transition, first producing mixed M3 and M4 hulls, then progressively shifting to all M4 production. By February 1942, the line was producing only Sherman tanks. December 7, 1941, changed everything, though the immediate impact on tank production was surprisingly limited. The Japanese attack on Pearl Harbor brought America fully into the war that had been consuming Europe and Asia for years. The cautious production ramp-up became a desperate race. The modest requirement for 1,000 tanks that had seemed ambitious in 1940 became utterly inadequate by early 1942. The Army's tank requirements exploded as military planners contemplated simultaneous operations in Europe, North Africa, and the Pacific. Chrysler responded by accelerating production through continuous optimization. The facility that had produced 4 tanks per day in September 1941 was producing 12 per day by March 1942. By July, 18 tanks daily rolled off the line. Each increase required solving bottlenecks that appeared as different operations struggled to keep pace with increasing tempo. A shortage of qualified welders threatened to slow hull production until Chrysler established dedicated welding schools that graduated 50 trained operators weekly. Machine tool availability limited component production until Chrysler secured priority allocations from tool manufacturers. Material shortages periodically disrupted schedules until supply chains were reinforced with buffer inventory and alternative sources. Owen Skelton, promoted to General Manufacturing Manager, established a system called Production Expediting. Teams of engineers monitored every operation on the production floor continuously, identifying bottlenecks within hours rather than days. When a problem was identified, resources were immediately redirected to solve it. If a welding station was falling behind, additional welders were reassigned from other tasks. If a machining operation was producing defects, engineers stopped production, diagnosed the issue, and implemented fixes before resuming operations. The culture at the Detroit Arsenal became intensely focused on production numbers. Daily totals were posted prominently where every worker could see them. People knew exactly how many tanks had been completed that day, that week, that month. Competition emerged between shifts, with each group trying to exceed the other's production. This competitive spirit drove continuous improvement as workers identified small efficiency gains that accumulated into significant time savings. December 1942 represented the culmination of everything that had been built over the previous 2.5 years. In that single month, the Detroit Arsenal produced 896 Sherman tanks and delivered them to the Army. This was 29 tanks per day, sustained for an entire month, a production rate that exceeded all other American tank plants combined. The Detroit Arsenal alone was outproducing the entire German tank industry and matching the output of major British facilities. The 896 tank month was not an anomaly or burst of temporary effort. It represented the optimized steady state of a production system that had been continuously refined. Every operation had been studied, improved, and standardized. The assembly line operated with mechanical precision, with tanks moving from station to station every 55 minutes. Workers performed their specialized operations with practiced efficiency built through thousands of repetitions. Suppliers delivered components with such reliability that inventory could be minimized. Quality control had evolved into a systematic science rather than craftsman judgment. The achievement proved definitively that tank production had been transformed from craft to industry. Military arsenals would never recover their monopoly on weapons manufacturing. The lesson was clear. Modern warfare required industrial methods, and private industry could deliver results that government facilities could never match. The success of the Detroit Arsenal created pressure for geographic distribution of production capacity. Military planners worried about concentrating so much capability in a single location. If sabotage or enemy action destroyed the Warren facility, American tank production would be crippled. Several additional tank plants were therefore constructed and brought online, including facilities operated by General Motors Fisher Body Division, Pressed Steel Car Company, and Pacific Car and Foundry. Each plant adopted assembly line methods and precision manufacturing principles pioneered at Detroit Arsenal, but none matched its production volume or efficiency. By war's end in August 1945, the Detroit Arsenal had produced 22,234 tanks of various models. This represented approximately 1/4 of all American tank production during World War II. The tanks themselves had evolved continuously. The Sherman went through numerous variants, each incorporating improvements based on combat experience and manufacturing lessons learned. The M4A1 featured a cast hull that simplified production at foundries. The M4A2 used twin diesel engines for improved fuel efficiency, particularly valued by British and Soviet forces. The M4A3 mounted the Ford GAA V8 engine, a purpose-built tank power plant. The M4A4 used the Chrysler A57 multibank engine. Later variants incorporated improved armor, better guns, and upgraded suspensions. Each change required production line modifications, yet the basic assembly process remained constant, demonstrating the flexibility that precision manufacturing and systematic production methods provided. The Sherman tank's historical reputation has been endlessly debated by military historians and enthusiasts. It was inferior to German heavy tanks like the Tiger and Panther in direct combat, with thinner armor and a less powerful gun. Sherman crews faced terrifying odds when encountering these heavier vehicles. The disparity in combat capability led to brutal losses and earned the Sherman a reputation as a death trap among some crews. But this analysis misses the crucial strategic context. Tank warfare is not primarily about individual vehicle duels. It is about maintaining operational tempo, sustaining logistics, and replacing losses. The Sherman excelled in these areas precisely because of how it was designed and manufactured. It was reliable, maintaining operational readiness far better than German tanks that were mechanically complex and prone to breakdown. It was easy to repair, with standardized components and well-trained maintenance crews. Parts were interchangeable and widely available. And above all, Shermans were available in overwhelming numbers. The production mathematics told the real strategic story. Germany produced approximately 24,000 main battle tanks from 1939 through 1945, an average of 4,000 annually across 6 years. The Soviet Union, with its massive industrial capacity focused almost entirely on military production, built approximately 105,000 tanks in the same period. Britain managed about 28,000. The United States, entering large-scale production only in 1942, built approximately 88,000 to 90,000 tanks by August 1945. The Detroit arsenal alone produced roughly 1/4 of American output in just 4 years. These numbers meant that the Allies could sustain armoured operations even with significant loss rates, while German forces struggled to maintain unit strength as attrition accumulated. An American armoured division that lost 20 tanks in combat could expect replacements within days or weeks. A German Panzer division that suffered similar losses might wait months for replacement vehicles that never arrived. This arithmetic of industrial capacity determined operational outcomes as surely as tactical skill or weapon design. After World War II ended, tank production at the Detroit Arsenal ceased temporarily as the facility transitioned to peacetime operations. The Korean War brought renewed military requirements. From 1952 to 1954, the arsenal produced 34,043 M48 Patton tanks. During the 1960s, it manufactured M60 tanks. In 1979, it began producing components for the M1 Abrams, which would become the primary American main battle tank for the next 40 years. In 1982, Chrysler Corporation, facing severe financial difficulties in its automotive business, sold its defense division to General Dynamics for $336 million. General Dynamics continued tank production at the Detroit Arsenal until 1996, when consolidation shifted final assembly operations to the Lima Army Tank Plant in Ohio. The Detroit Arsenal site today hosts the United States Army TACOM Life Cycle Management Command and the Combat Capabilities Development Command Ground Vehicle Systems Center. A Michigan historical marker at the site commemorates its role in transforming military manufacturing. The people who made the Detroit Arsenal possible went on to varying fates. Kaufman Thuma Keller continued leading Chrysler through the war years and the challenging transition to peacetime production. He became chairman in 1950 and retired in 1956, respected as one of the key figures who had armed America for modern war. Albert Kahn, the architect whose building made mass production physically possible, died on December 8, 1942, just months after seeing the Detroit Arsenal reach peak production. His architectural innovations influenced industrial construction throughout the remainder of the 20th century. William Knudsen served throughout the war in uniform, commissioned as a lieutenant general in the United States Army on January 28, 1942, the highest rank ever given to someone not already in military service. He died in 1948. The Sherman tanks built at the Detroit Arsenal served in every theatre of World War II. They landed on Normandy beaches on D-Day, spearheading the liberation of Europe. They fought across France and Germany. They island-hopped through the Pacific with Marine Corps units. They equipped British, Canadian, Free French, Soviet, Polish and Chinese forces under Lend-Lease. The global reach of American industrial production meant that Shermans fought on every continent except Antarctica and Australia. Many Sherman tanks survived the war and continued in military service for decades afterward. Israel used extensively modified Shermans in the 1967 Six-Day War and the 1973 Yom Kippur War, upgunning them and improving their armor. South American nations operated Shermans into the 1980s. A few remain in running condition today, preserved by museums and collectors as monuments to an era when industrial capacity determined military power. The transformation of tank manufacturing from craft to industry happened because engineers and industrialists refused to accept conventional wisdom about what was possible. They recognized that tanks and automobiles were fundamentally similar as mechanical assemblies, both comprising thousands of components that needed to fit together precisely. This insight, obvious in retrospect, was revolutionary in 1940. It required looking past surface differences to see underlying similarities. It required engineering courage to redesign military equipment despite military resistance. And it required industrial confidence to commit to production methods that had never been attempted at such scale. The success of the Detroit Arsenal validated principles about mass production that had been developing for decades in civilian industry. Henry Ford had demonstrated that interchangeable parts and moving assembly lines could produce automobiles at unprecedented volume and low cost. Chrysler extended these methods into a new domain, proving they could produce instruments of war with equal efficiency. This possibility transformed World War II's outcome. Without mass-produced tanks, American ground forces would have fought at severe numerical disadvantage against enemies who had been building armored forces for years. Britain would have struggled to replace combat losses and maintain armored divisions. The Soviet Union, despite its enormous industrial capacity, benefited significantly from thousands of American-made Shermans that supplemented domestic production. The ability to produce nearly 90,000 tanks in 4 years was unique to American industrial capacity, and roughly a quarter came from a single facility in Warren, Michigan. The invisible achievement was perhaps greater than the visible one. The Detroit Arsenal did not just build tanks. It proved a concept. It demonstrated that private industry could solve government problems faster and more efficiently than government could solve them internally. It showed that engineering expertise mattered more than military tradition. It validated the idea that American industrial capacity, if properly mobilized, represented a war-winning advantage that enemies could not match. This validation shaped post-war American strategy profoundly. The concept of maintaining industrial capacity that could be rapidly converted to military production became central to Cold War planning. The idea that American industry could outproduce any potential adversary became accepted doctrine. The relationship between private contractors and military procurement that began with the Detroit Arsenal contract became permanent structure that persists today. The arsenal of democracy concept that Roosevelt had articulated became institutionalized reality. The engineers who made the Detroit Arsenal possible were practicing systems thinking before that term existed. They did not solve individual problems in isolation. They designed an entire system where components, suppliers, workers, assembly processes, quality control, and logistics functioned as an integrated whole. Each element was optimized not independently, but as part of the larger production system. This holistic approach was visible in countless details. The sunken assembly line trench eliminated bottlenecks in undercarriage work. The supplier network created resilience through geographic distribution. The training system created a pipeline of skilled labor that could replace losses and support expansion. The system was designed to scale from the beginning. When production needed to double, The system absorbed that increase by adding shifts, expanding supplier orders, and training more workers. When new tank variants were introduced, the system adapted by modifying fixtures and updating procedures. This flexibility was a direct result of precision manufacturing and systematic production methods. Craftsman production required rebuilding institutional knowledge and retraining workers for each significant design change. Assembly line production simply required engineering work to update processes and tooling. The ultimate measure of success was efficiency improvement over time. The first M3 tank, completed in April 1941, required approximately 500 man-hours of direct labor. By December 1942, M4 Sherman tanks were being assembled in approximately 150 man-hours. This productivity improvement of more than 300% came from relentless optimization. Every month, industrial engineers studied production data, identifying operations taking too long or producing defects at high rates. They analyzed why workers struggled with particular tasks and redesigned fixtures, tools, or procedures to make the work easier and faster. They questioned every assumption, asking whether there was a better way. This culture of continuous improvement was alien to military arsenals accustomed to unchanging procedures handed down over decades. But it was essential to achieving production volumes that the scale of modern warfare demanded. The war would not wait for perfect processes. Good enough processes that could be implemented immediately and improved continuously were far more valuable than perfect processes that took years to develop. The financial investment in the Detroit arsenal was substantial but modest compared to the facility's output. Initial construction cost approximately $20 million. Equipment and tooling added another $30 million. By war's end, total investment exceeded $100 million. But the 22,000 tanks produced represented a value exceeding $2 billion at contemporary prices. The return on investment was enormous by any measure. More significant than financial return was strategic value that cannot easily be quantified. The Detroit arsenal's production capacity allowed American ground forces to fight with numerical superiority in armored vehicles, which proved crucial in campaigns from North Africa to Germany. Armored divisions could sustain operations knowing that losses would be replaced. Commanders could take tactical risks that would have been impossible without assured resupply. The psychological impact on enemy forces of facing seemingly endless numbers of tanks cannot be overstated. The story of the Detroit arsenal is ultimately about seeing possibilities that others missed. When Kaufman Thuma Keller told William Knudsen that he had never seen one of these things, he was acknowledging ignorance without conceding defeat. Chrysler's engineers did not know how to build tanks, but they knew how to build complicated mechanical assemblies from thousands of components. They knew how to manufacture precision parts. They knew how to organize production lines. They knew how to train workers. This confidence that engineering principles could solve any production problem was characteristically American and profoundly consequential. European manufacturers had accepted that tanks were fundamentally different from civilian products, requiring specialized government facilities and master craftsmen. American industrialists saw only machines that could be broken down into components, processes, and assembly sequences. This philosophical difference in how production problems were framed made all the difference in outcomes. The Detroit arsenal validated the American approach completely. In 9 months, Chrysler went from zero tank knowledge to delivering finished vehicles. In 18 months, they were producing tanks at rates exceeding initial requirements. In 3 years, they had delivered more tanks than most nations produced in the entire war. The engineers and workers who made this achievement possible were mostly ordinary people doing extraordinary work. They were not heroes in the conventional sense. They did not fight battles or liberate occupied territories. But they built the tools that made those achievements possible, and in doing so, they demonstrated that industrial capacity properly applied could determine the outcome of modern warfare. This democratization of military production was itself revolutionary. In previous conflicts, weapons came from specialized arsenals operated by master craftsmen, with production limited by the availability of rare skills. In World War II, American weapons came from automobile factories, appliance manufacturers, and dozens of civilian industries that converted to military production. The workers were housewives, recent high school graduates, farmers, and shop clerks who learned specific operations and performed them competently. Skill was designed into the production system rather than residing in individual craftsmen. The Detroit Arsenal symbolized and proved this transformation. It showed that private industry could build military equipment more efficiently than government arsenals. It demonstrated that production methods developed for civilian goods could apply to weapons of war. It validated Roosevelt's arsenal of democracy concept. And it established that industrial capacity was as strategically important as military tactics or advanced technology. The legacy persists today in ways both visible and invisible. Modern military procurement still relies heavily on private contractors using civilian manufacturing methods. The M1 Abrams tank, America's current main battle tank, is built using production techniques that descend directly from those pioneered at the Detroit